Hey everyone, today we are going to learn about classification, logistic regression, decision boundaries, and then implement logistic regression from scratch, just like we did in our previous regression videos. So, before we begin logistic regression, let's learn about classification. Classification problems are one in which, based on data, you predict the value as binary. For example, the output may be yes or no, this or that, true or false, or even 0 or 1. Thus, output y could be one of two values only, and this is called binary classification. So for example, you want to predict whether the email is spam or not, the answer could be either yes or no. Or the transaction is fraud or not, again the answer may be yes or no. And logistic regression is a type of a classification model. Now, you may ask that, Riken, how is it different from linear regression? So, in linear regression, we predict a number like we did in the house price example, but in logistic regression, output is binary only. It ranges between two values, generally 0 and 1, where 1 means higher probability of the problem and 0 being the least. So, if you want to predict price of house based on feature, revenue based on ads, estimating student grades based on past data, you may want to use linear regression and logistic regression to see whether email is spam or not, cancer is malignant or not, is the images of cat or not. And by the way, even big firm use this algorithm to show us ads based on the probability whether we may like it or not. Now finally, let's dive deep into logistic regression. In linear regression, we use equation y equal to w time x plus b, and y was our prediction based on optimal weight and bias. However, in logistic regression, we use a slightly different function, and that is called sigmoid function, and it is written as g of z equal to 1 upon 1 plus e to the power minus z, and g is always between 0 and 1, where z is equal to w times x plus b. Yes, you're not hearing it wrong. We pass prediction from linear regression to the sigmoid function to predict our outputs. By the way, we can also use dot product formula for multiple linear regression instead of w times x plus b. On screen, you see our graph for sigmoid function, and you can see for larger value of z, it is close to 1, and for very small values of z, it is close to 0. So let's say if z is minus 500, the prediction would be close to 0, and if z is 500, it will be close to 1. If you see our graph, you will get a question in your mind. What if output comes to be 0.5? And that's a good question. So for our logistic regression model, we always set a threshold value like 0.5 or 0.6. So if prediction is equal to or above 0.5 or 0.6, it is considered as 1, and below that as 0. Now let's see a small concept called decision boundary. On screen, you see a dataset with two features x1 and x2, and those circle and axis are value of y. And you may draw this line right here to separate both classes, and this is exactly what we call a decision boundary. For more complex graph, decision boundaries may change and look like this, or even this. Now let's see the cost function for logistic regression. In the linear regression, we simply use this function where we added the squared difference between predicted value and original value for all the data and divided by m, and we called it squared error cost function. But in logistic regression, it's not quite that easy. Instead of a square error cost function, we use this. Yes, it's a pretty big equation, but don't worry, this is the simplified formula. The original one can be very confusing and difficult if you're not into maths. Here's a point to note, f of x is exactly as g of z we saw earlier. Now let's finally see the gradient descent for logistic regression. We write gradient descent as, yes, it is exactly the same as linear regression. So what has changed? The changed thing here is f of b. Here, f of b is sigmoid function from earlier and not w times x plus b. And that's it. We have learned the concepts of logistic regression. A few things we saw earlier like vectorization and feature scaling can also be applied here. Now let's dive deep into code and see how we can implement our algorithm. And today also we won't be using scikit-learn or any library, just pure Python and NumPy. Let's start by importing the NumPy module. Now let's define the Sigmoid function with argument z. We return 1 upon 1 plus np.exp of minus z. Here we use NumPy's exp function to compute the value of e to the power minus z. This gives us an output between 0 and 1. Next, let's define the cost function and pass x, y, w, and b as arguments. First, we get the number of training example using the number of rows in x. Then we compute z using the dot product of x and w and then add b. We pass z into the sigmoid function to get the predicted probabilities. After that, we calculate the logistic loss using the binary cross entropy formula. Finally, we divide by the number of training example to return the average cost. Now let's define the gradient computation function, again passing x, y, w, and b. We compute z the same way, applied sigmoid to get prediction and then calculate the error as predicted minus actual. Using that error, we compute the gradient with respect to w by multiplying the transpose of x with the error and dividing by the number of examples. We compute the gradient with respect to b by taking the average of the error values. Then we return both gradients. Next, let's implement the gradient descent algorithm. We pass x, y, initial w, initial b, learning rate alpha, and number of iterations. We run a loop for the given number of iterations. Inside the loop, we compute the gradients and update w and b by subtracting alpha times their respective gradients. We will use the gradient descent function from above. Every 100 iteration, we print the current cost to monitor training. After completing all iteration, we return the final values of w and b. Now let's define the predict function. This is a helper function. We compute z using x, w, and b, apply the sigmoid function to get probabilities, and then convert those probabilities into 0 or 1 using the threshold of 0.5. After defining all function, we create a training dataset with 2 features per example and corresponding binary labels. We also define a small test dataset with its label. Then we initialize the parameters. Weights are initialized to zeros based on the number of features. Bias is set to 0, learning rate is set to 0.1, and number of iteration is set to 1000. Now let's finally train the model by calling the gradient descent algorithm function with the training data and initialized parameters. Let's return the final learning weight and bias, and let's print the values of w and b. Now let's use the new values of w final and b final and use it on our training data to see if it's working or not. Now let's also use it on our test data and predict the values. So we're done defining our algorithm. We defined all the functions like sigmoid, compute cost, compute gradient, the gradient descent algorithm, the helper function, and the training dataset. Then we also initialized our parameters and then finally run the algorithm. If you see iterations, the cost has gone significantly, and these are the final values of W and P. For our training data, however, the training prediction were 100% accurate, And for the test, they turned out to be accurate as we defined earlier. And we are done. We understood logistic regression and implemented it from scratch. Thanks for watching. I'll see you in the next one.